Hi, welcome to the Dimanex team SAS Hackathon jury video.
Hi, I'm Tom from Dimanex, and along with the rest of the Dimanex team, we're really excited to share with you the work that we've done with SAS for this year's hackathon to look into optimizing supply chains with additive manufacturing. Hope you enjoy.
Global supply chains enable us to buy products and run our businesses with components from all over the world. Our businesses and nations are increasingly reliant on systems and processes that facilitate delivery of goods, with ever-increasing reliance on warehousing and global shipping. But what happens when things go wrong? In an age of increasing geopolitical uncertainty, natural disasters, and even a global pandemic, we've seen these systems straining, causing an increase in the cost of goods that we buy and, in some cases, the collapse of businesses. But what if there was another way? Rather than producing a large quantity of parts on the other side of the world, then moving them thousands of kilometers to be stored in a warehouse, wouldn't a more sustainable, resilient solution be to produce only the parts we need in a location close to where they are needed? With no minimum order quantities and the ability to distribute manufacturing globally, additive manufacturing, also known as 3D printing, can facilitate production of parts from a digital library locally to where they are needed, providing a less wasteful, more sustainable, and resilient solution for the decades to come. However, additive manufacturing is still a more expensive option in most cases. Before investing time, money, and resources into 3D printing efforts, the business case and sustainability effect of 3D printing are required based on which sound supply chain decisions can be made. So, what if we could estimate accurately, based on readily available data, the cost to purchase parts using additive manufacture?
This is where Dimanex and SAS come in. So Dimanex has spent around 9 years optimizing supply chains for customers using additive manufacturing, and in that time, we found that around 8 to 20% of parts typically have a business case for AM. We've been able to help customers reduce waste in lead time, stock, inventory, and transport, and also make further savings by helping them redesign parts to really embrace additive manufacturing. We've been able through this time to be able to accrue 60 million data points, which we've been able to leverage with SAS in order to create powerful machine learning models which give instant results on the total cost of ownership for customers so that they can really quickly identify the parts which are going to bring them the most benefit through additive manufacturing today.
In order to provide Dimanex customers with data that they need to make good decisions around AM, we need prior knowledge of how much parts could potentially cost in AM. First, the hackathon team analyzed existing Dimanex customer data and supplier prices to find trends and patterns. Next, decision tree models were created to choose materials based on previous data. With this, linear regression models could be created to predict what part prices would be in appropriate AM technologies. Finally, the results can be added to the Dimanex platform to fully calculate total cost of part ownership.
Initial analysis of the dataset that was prepared from the Dimanex platform showed clear correlations between a number of data points and the purchase price of the parts. Analysis with SAS was quick and easy. Once data was uploaded, it could be quickly organized into drag and drop visualizations which quickly enabled better insights. With a large variability between processes and materials, it was decided to attempt to create linear regression models in order to predict purchase price based on different materials. For many of the hundreds of materials, there was only a small amount of relevant data, so where there were less than 50 relevant lines of data, models were not created.
Using SAS creating a decision tree model from the data was extremely straightforward. Especially given that data from customers is not often organized or accessible in similar ways, being able to quickly build models where missing data can be controlled with missing assignments was extremely useful. From the test dataset, only around 0.5% of parts had enough data to get results from the model without being able to apply rules around missing assignments. Another feature of the analysis was being able to understand the factors that affect material decision, including the most relevant data points to determine each material. Once analyzed, the models performed well and predicted AM materials fit close with the actual AM materials from the test data.
Much like creating the decision tree models, working with SAS to create linear regression models was fast. creating models based around available data, with missing data not deflecting the model and allowing predictions to be made in these cases, produced extremely valuable models for Dimanex and our customers. When looking at the initial models, some cost predictions were negative, for example prices predicted like -€20. While some degree of error can be expected in an estimation, negative purchase price predictions would impact badly on any follow-up analysis of business cases, because it would be impossible to find a provider who would pay a customer to produce parts. In order to get around this and improve the models, data points that had a strong correlation to part purchase price were converted to their natural log values. This meant that the intercept of the predicted regression line would fall much closer to zero, and also meant that the data was much more evenly distributed, resulting in a much better predictive model. Overall, the models created presented good scores for accuracy. Across a test dataset of 4,500 items, the models scored an R-squared value of 0.78 across all the different models, and for the most common material, which represented around 40% of all data, had an R-squared value of 0.84.
Overall, the material predicting decision tree and follow-up linear regression models to predict pricing produced good results. With this data, it's possible now for Dimanex to use this to provide immediate price indication, and therefore more informative costs to customers around the total cost of ownership should they choose to adopt AM. Without this, there are more barriers to AM adoption and its associated benefits. By immediately indicating the total cost of ownership through Dimanex and SAS, customers know where to digitize parts for additive manufacturing so that they can embrace the benefits of lead time, inventory cost, and CO2e reduction. Customers can now get parts made through a distributed network anywhere in the world for a more resilient supply chain. Thanks for watching. Learn more at Dimanex.com.